Hello, dear viewers. Today, we will talk about the origins and evolution of string theory, the implications of the multiverse, and the fundamental problems in string theory. Susskind initially focused on explaining the strong nuclear force which holds protons and neutrons together in the atomic nucleus. The innovation was to conceptualize particles not as point-like entities, but as one-dimensional strings, whose interactions and vibrations give rise to the phenomena observed in particle physics. In the mid-1980s, John Schwarz and Michael Green expanded on Susskind's ideas, proposing that string theory could unify all known fundamental forces: strong, weak, electromagnetic, and most importantly, gravity. This was particularly important because gravity had shown resistance to inclusion in the quantum framework provided by the Standard Model of particle physics. String theory represents a rich mathematical structure that requires the existence of additional spatial dimensions beyond the 4 dimensions, 3 of space and 1 of time. These extra dimensions are assumed to be compressed or tightly coiled at scales too small to be detected by current experimental methods. By the 1990s, it became clear that string theory could describe not just a single universe, but many possible universes with varying physical laws. This scenario is often referred to as the string theory landscape. These multiple solutions emerged from different possible shapes and sizes of compressed dimensions, leading to the multiverse scenario, where each solution corresponds to a different universe. The large number of potential universes allowed by string theory, 10 to the 500th power, as Susskind puts it, presents both a theoretical richness and a crisis. This landscape problem suggests that if every mathematical solution corresponded to a physical universe, the predictive power of string theory would be severely weakened. The current state of string theory and its implications for the multiverse hypothesis require further investigation of the initial conditions of the universe. The question of how these countless possible universes might physically manifest depends on our understanding of the origins of the universe. This requires revisiting cosmological models of the early universe and potentially integrating ideas from inflationary cosmology, quantum gravity, and string theory. Initially, Susskind's goal was specifically more focused on explaining the strong nuclear force which is responsible for binding protons and neutrons together in the atomic nucleus. Susskind arrived at a mathematical formula that offers greater consistency when particle interactions, especially collisions between pairs of particles, are visualized not as point-like interactions, but as interactions between looping, oscillating strings. These strings would come together temporarily, oscillate in unison, then separate again. This insight triggered a moment of profound awareness in Susskind, vividly reflected in his reflections in Cosmic Landscape. Yoichiro Nambu and Holger Nielsen independently came to similar conclusions simultaneously. The scope of string theory expanded significantly in 1984 with the work of John Schwarz and Michael Green. Their research suggested that string theory could potentially unify the strong, weak, and electromagnetic forces under a single theoretical framework and, intriguingly, suggested the existence of a hypothetical graviton predicted as the quantum carrier of gravity. This was particularly important because gravity had consistently avoided integration into the Standard Model, the dominant theoretical framework describing the fundamental forces and interactions between particles. This extended string theory has begun to attract significant attention due to its ability to potentially reconcile inconsistencies between general relativity, which governs macroscopic gravitational forces, and quantum mechanics, which governs the subatomic world. Despite its aesthetic and theoretical appeal, string theory required the acceptance of concepts that went beyond the traditional. It required theorists to postulate at least 10 dimensions, 6 or more beyond the usual 3 spatial dimensions and 1 of time. It is theorized that these additional dimensions are compressed and hidden from direct observation, like complex folds in origami. The theory became increasingly complex as it developed in the 1990s. The emergence of higher dimensional entities called branes and various other components such as streams revealed that string theory could describe not just a single universe, but a multitude of possible universes, each with its unique physical laws and constants. This landscape of solutions, potentially potentially numbered at Google levels, suggested a multiverse scenario that challenges the idea that string theory could lead to a precise description of our universe. This proliferation of possible universes posed a philosophical and scientific challenge. If every mathematical solution of string theory corresponded to a physical reality, the theory ran the risk of becoming unfalsifiable, offering explanations rather than predictions. Then the radical idea emerged that perhaps there was no correct geometry for these extra dimensions. Instead, every theoretical possibility could be a realized physical universe. Despite these advances, string theory failed to provide a mechanism that would enable these different universes to truly materialize, leading Susskind to distinguish between mathematical and physical existence. Rich in solutions, the theory did not explain how these universes emerged or why our universe has its unique physical laws. To go further, physicists recognized the need to explore the earliest moments after the Big Bang and aim to understand how the conditions of the early universe might have selected our specific physical reality from among the countless possibilities offered by string theory. This ongoing search for the origins of our universe remains one of the most profound challenges in modern physics. Thank you for listening. Stay well.